Swayam Prabha. Digital India. Educated India.
Let me begin by thanking Raj and his colleagues on the organizing committee for the very kind invitation to come to this wonderful location and to contribute to this celebration of the scientific career and contributions and birthday of Professor Satyamurthy. It's a real pleasure to be here. I'm going to tell you an experimentally led story, but there will be some theory in here, I promise. It's going to be looking at a photochemical process from three different perspectives, two experimental and one computational, to try and get a deep understanding of a photochemical reaction, which I'll tell you about first. So let me define the system that we're going to study, and then I'll explain how we have studied it. So the system we have been looking at is the photochemistry of so-called diazo compounds. These are molecules like this one here, where we have a nitrogen, an N2 moiety bound into an organic molecule. And it's well known in the organic chemistry community that if you photoexcite these with ultraviolet light, they release nitrogen and they form carbene species. So here drawn as the singlet carbene because this is a singlet parent molecule, and spin conservation and the photodissociation will give us a singlet carbene. But there are low-lying triplets and other singlet states of this carbene species. Now, if we modify this molecule to include a carbonyl group adjacent to the diazo group, so a so-called alpha-diazocarbonyl compound, then the photoexcitation can lead to the carbene, but it's also well known that a product of that photochemistry is this ketene molecule, and this molecule is synthetically useful because it can be used in cycloaddition reactions. So the organic chemists have wondered about this and proposed two routes from here to this ketene. One is that in a concerted fashion, this group here, this R1 group, migrates to this carbon atom at exactly the same time as this nitrogen is leaving, and that gets you straight to here. And so that's a concerted mechanism. But the alternative is that this nitrogen molecule is lost first to make the carbene, as in this prototypical photochemistry, and then after that, the R group here migrates here. And both end up in the same place, but the question is, which mechanism gets you there? So there's a sequential versus a concerted possibility of process here. So I'm going to tell you three ways we've studied this question. First of all, I'm going to tell you about ultrafast X-ray scattering, so a structural probe to try and look at the structural changes in these molecules in real time on an ultrafast timescale. And then I'll tell you how we've tackled this problem with computational chemistry in collaboration with a colleague of mine at the University of Bristol, and use that to simulate the data that we obtain experimentally from the X-ray scattering. And then finally, if I leave myself enough time, I'll tell you how we've studied this reaction in solution. So these are gas phase experiments, gas phase calculations, but we've also looked at this experiment in solution. I'll explain how we've done that and what we learned from contrasting the dynamics in the gas phase and in solution. So let's begin with the ultrafast X-ray scattering. This requires a very extensive piece of apparatus. This is an X-ray free electron laser. So this is LCLS, This is LCLS in California, located near to Stanford University at SLAC in California. So it's about a 3 kilometer long electron accelerator which generates coherent X-ray pulses. And those X-ray pulses are about 35 femtoseconds long. So they can be used for ultra-fast X-ray scattering experiments. And so we did experiments on this diazocarbonyl compound, or one of these, led by Felix Alum, who was a staff scientist at that time at LCLS, inspired by the PhD work from my student Ryan Phelps in Bristol, which I'll tell you about at the end of the talk. And I'll talk about theory from my colleague Basil Kershaw in a little while as well. So this is the concept of the experiment. I'll get the hang of this in a moment. We take a low vapor pressure of this particular diazo compound, so I'll call this EDA, ethyl diazoacetate. So we have a few millibar of pressure of that in the gas phase. We photoexcite that with a femtosecond UV laser pulse, and that initiates the photochemistry in these molecules. And then we come in with approximately 10 kilo electron volt hard X-ray pulse, about 35 or 30 femtoseconds in duration, and scatter those X-rays off the photoexcited gas. And this is now an X-ray scattering problem, which should tell us about structural information and the evolution of the structure of these molecules. So the measurable in this experiment is on a position-sensitive detector. You measure the scattering angles of the elastically scattered X-rays, and those relate to the momentum transfer of the X-rays as they're scattered from the gas phase molecules. And the momentum transfer is inversely proportional to pairwise separations of atoms in the molecule. So as the molecule evolves in structure and the distances between the atoms evolve, then so the scattering pattern should change, as measured by this momentum transfer Q. So this is a schematic of the experiment. We start with the diazo compound, this EDA molecule. It has syn and anti-conformers where the N2 is either opposite to the carbonyl or on the same side as the carbonyl, and those don't rapidly interconvert. There is a barrier to that interconversion. We photoexcite them, and we're either going to go straight to the ketene by direct loss of N2 and concerted migration, or we're going to go stepwise through the carbene and end up at the ketene. So I hope you can see this. I'll show you another representation of this data in a minute, which may make it clearer. But this is the experimental observable. So here's the scattering, the momentum transfer along the x-axis and time delay along the y-axis. And the time delay here is going up to 1 picosecond. So we have sub-picosecond. We have better than 100 femtosecond time resolution in this structural study. Negative going features here are depletion signals. So these are changes in the scattering pattern that we're plotting here. So negative features are depletions, blue features are depletions, and red features are new internuclear or interatomic separations that are developing from the photochemistry. So perhaps easy to see on the screen, these are lineouts. So these are cuts through this data set at different time delays, plotted in different colors, and the black arrows are showing you the evolution of the scattering in the system. So you can see that this deep feature here, this blue feature here is developing at small q, and this feature is growing in at larger q as this red feature here. So that's the experimental observable. This contains structural information, but we can't just read off the structural information. We need to somehow interpret that. And the way that we do that, or one of the ways that we do that, is to fit each of these lineouts from this data set to a pair of basis functions. And these basis functions describe the momentum transfer that we would expect to see if we had the carbene shown in green, or if we had the ketene shown in yellow. So these are the scattering patterns we'd expect for those two species. We can decompose this data set by fitting to those basis functions. And that gives this analysis here, whether you see the green color growing in here and then decaying, and as it decays, the yellow feature grows in. So that's, the data are telling us, according to this analysis, that the carbene comes first and then decays, and as it decays, the ketene evolves. So the data, at least in that analysis, are pointing to this stepwise mechanism for the photochemistry. All right, so then we turn to computational methods to try to understand what's going on. So we treat the photoexcitation of the EDA using electronic structure calculations. These are the plots of the occupied and non-occupied frontier orbitals in the system, and the dominant absorption in this in the UV for this species is from this non-bonding type orbital localized largely on the oxygen atom into this antibonding pi star orbital localized in plane on the N2 part of the diazo compound. So that gives rise to the strong absorption band in the UV spectrum. The other excitations on this that are possible on this between these sets of orbitals have zero oscillator strength, at least in the level of calculations used. So that's the excitation. That gives rise to this S2 state shown in green here. The adiabatic S2 state has, in the Frank-Connon region, has this N pi star character. So we photoexcite to that, but nearby there's another excited state, this S3 state, and there's a lower-lying S1 excited state in the Frank-Connon region with pi star character. And so, as Professor Salfrank has just told us about, we have conical intersections between these adiabatic potential energy surfaces, and so the molecules can evolve adiabatically along here, reach this conical intersection, and cross onto the adiabatic S1 potential energy surface. And that's their route for relaxation, because they then find another conical intersection with the ground state, and the N2 dissociation occurs somewhere in the region of this second conical intersection. So that's the photochemical pathway. The molecules could in principle relax back to the parent molecule, but they can also go on to fragment and isomerize. So these are calculations using CAS-SCF methods to characterize the potential energy curves. These are XMS CAS-PT2 calculations, which show largely the same thing as the CAS-SCF calculations, but both of these are too expensive, at least, or were at the time, for us to propagate trajectory simulations. So we benchmarked TDDFT calculations against the high-level wave function methods, and the TDDFT gives a good enough description of the potential energy surfaces for us to use them in the simulation. So I'm going to tell you about trajectory simulations done by Kenzo Mamarat and my colleague Basil Kursho using these TDDFT-based potential energy surfaces. And we are very aware that that gives a poor description, particularly of the conical intersection with the ground state, but we have ways to try and avoid that problem in the calculations. Kenzo and Basil were able to propagate 86 trajectories at that TDDFT level of theory. You can see the evolution here. So the green is the population of the S2 state decaying very quickly. The non-adiabatic trajectory surface hopping is taking the population into the S1 state, which is shown in blue here. That rises very fast and then decays. And then in purple, perhaps you can see the growth of the S0 state population. And by comparing internuclear distances in the molecule at each step in these simulations, they can categorize the structures as either the parent molecule or the carbene or the ketene. And so what you see here is the decay of the parent molecule, growth of the carbene in blue, and then that decays, and you see the growth of the ketene at later times. So the trajectory simulations are reproducing broadly what we deduced from the analysis of the ultrafast X-ray scattering data, that this is a stepwise mechanism in which the carbene forms first, and then there is the rearrangement to the ketene. But that's all happening on a very fast time scale. This carbene is growing in a few hundreds of femtoseconds and decaying in a few hundred more femtoseconds. So these are sub-picosecond dynamics. We can analyze trajectories and plot them out in this form here. So these are various interatomic separations as a function of time. So what you can see here, the dashed lines are carbon-nitrogen distances. So this carbon to one of these nitrogens. And there's this very rapid initial jump, which is the loss of the N2 from the molecule. And then the molecule evolves in time as shown about here. This is now an oxygen-oxygen separation. So that's this distance between these two oxygen atoms. This distance here corresponds to this parent-type structure. And then there are rapid jumps to this longer oxygen-oxygen separation when this group here migrates to here for this Wolff rearrangement reaction, and we get the ketene. So this jump up to here is the formation of the ketene, and this large amplitude motion you can see here is because that ketene is formed with very high vibrational internal energy. So it's a highly exothermic process. It's putting a lot of energy into vibrational motion of the ketene. This is then the calculation of the pairwise distribution function for atomic separations from these trajectory simulations. And you can see various features in here, like the loss of the N2 is this light feature down here. And these blue features are depletion of two carbon-nitrogen distances. So these are the loss of this carbon-nitrogen distance and then the second carbon-nitrogen distance. So this pairwise distribution function can be inverted to give the momentum transfer data. So the observable from the X-ray scattering. So I'll tell you about that in a moment. That's the next step, to go from the computational dynamics to the simulation of the X-ray data. And again, I hope this contrast comes out well enough on the projector. This is the experimental data set that I showed you earlier on. This is the theoretical prediction based on the trajectory simulations. And qualitatively, at least, it's pleasingly similar. There are lots of similarities between these two patterns, and we can do more quantitative comparisons than just admiring the similarity. We find by more quantitative comparisons that there is very good agreement between these two data sets. So it would appear that the theory is giving a good description of the experimental observations. And so if that's right, and the theory is correctly capturing the dynamics, even with the TDDFT-based potentials, then here is our description of what's going on. We're photoexciting to the S2 state, that's the bright state in green. There's non-adiabatic evolution through 2 conical intersections, and then fragmentation by loss of nitrogen. And then there is this stepwise rearrangement. And you can see the time constants for that. The growth of the carbene is in about 230 femtoseconds, and then that decays in about 770 femtoseconds, and isomerizes to the ketene species. All right, so that's the story for the gas phase. But we've also been able to study this photochemistry in solution. We can dissolve our EDA molecule in an organic solvent of our choice, and we can photoexcite it with a UV laser pulse, a femtosecond UV laser pulse, and come in with a broadband infrared laser pulse and look with time-resolved infrared spectroscopy at the evolution of the system. So I have to now reorient you. We're now no longer using a 3-kilometer long X-ray free electron laser. We're now using a standard benchtop ultra-fast femtosecond laser system in my lab in Bristol. We're generating femtosecond UV pulses and femtosecond infrared pulses and propagating them through a flowing solution, photoexciting the molecules, and then probing with time-resolved infrared spectroscopy what's going on in the solution. The data that I'm going to show you have this general form. I'm going to show you changes in absorbance of the infrared light. So the infrared is our probe. We're going to measure the change in absorbance of the solution caused by the photoexcitation with the UV pulse. And so positive going features in these spectra are going to be new products of the photochemistry or excited state intermediates. And negative going features are going to be depletion of the parent molecule. So these are time-resolved infrared spectra obtained in the ketene region. This is a slightly different compound from the one I've been talking about so far, but the photochemistry is the same. So this molecule, 256 nanometers, isomerizing to the ketene. And so if we probe, we tune our infrared laser to the ketene infrared region up here at about 2100 wave numbers, we see the ketene band growing in over time. So we're seeing photochemical production of the ketene. There's lots going on here, and this data set over here is exactly the same data set, just represented in a different way, just in this color map rather than as time slices. The time slices are evolving from purple through blue to green and red at later times. So that this black arrow is showing you the time evolution of the system. But what you're seeing here is the vibrational cooling of the ketene. I told you before that this ketene is formed highly vibrationally excited, and now the molecule is in solution, it can have that vibrational excitation quenched by coupling to the solvent. And so that takes a few picoseconds or tens of picoseconds, and we see that as a shift in the infrared band until it settles down into the characteristic frequency of the ketene fundamental stretch. So we see those dynamics. We clearly see the ketene form, and it's forming in a few tens of picoseconds, actually rate determined by the vibrational cooling rather than the photochemistry. But we can also demonstrate that the photochemistry is going through a carbene, and we can do that by trapping the carbene chemically. Organic chemists know that if you generate a carbene like this one in a nucleophilic solvent, so in this case tetrahydrofuran, this carbene is electrophilic, the solvent is nucleophilic. They want to get together, and if they do, they make this species here, the zwitterionic species, which is known as an IIID species. And this has a characteristic infrared band of this carbonyl group because it's conjugated into this negative charge here, and that downshifts in frequency the carbonyl stretching mode. And so we see that distinctly here at quite a low carbonyl stretching frequency. We see the growth of this feature here. So now in this color map, red colors are growth or are new positive features that are growing in, and blue colors are depletion of the parent molecule. So we're seeing the growth of the IIID species, and it's happening on a time scale of a few tens of picoseconds that's limited by the bimolecular chemistry that's taking place here. So we have definitive evidence that we're forming the carbene species in this photochemistry. We can actually study the solvation dynamics around that IIID that's forming. The IIID has this zwitterionic character, and so the solvent will respond on a fast time scale to the solvation of a zwitterionic rather than a neutral species. or at least a less polar species. And so we can study those dynamics by doping our THF solvent with a little bit of ethanol. So we introduce a protic solvent, and we see diffusional coordination of the ethanol to the illid species. You can see it here in this spectrum as a shift to an even lower wave number of the carbonyl band. So what's going on there is that we're forming the illid species here, and ethanol is diffusing into proximity with that, forming a hydrogen bond to the carbonyl group, and that hydrogen bonding reduces even further the frequency of the carbonyl stretch. And so we can see the growth of that solvent complex in solution in real time in terms of the shifts in the infrared bands that we're recording. So we get a very detailed picture of the photochemistry in solution. We can also look at other chemistry. Carbenes are quite promiscuous in their chemistry. They will react by insertion into chemical bonds, and we can see the carbene in this case here inserting into a CH bond in tetrahydrofuran and giving another carbonyl shifted band, this one shifted to higher wave number appearing in the spectrum, and we attribute that to this bond insertion product of the carbene chemistry. So, I'm just about done. What I've shown you is that we can study gas phase structural dynamics on ultra-fast timescales if we photoinitiate a reaction with a femtosecond laser pulse and we probe with an X-ray pulse which has comparable time resolution. So if we make use of a 30 femtosecond coherent pulse of X-rays from an X-ray free electron laser, we can look at the structural dynamics occurring in photoexcited molecules. And we've done that in this case for this Wolf rearrangement reaction. The patterns, the scattering patterns we get are not directly interpretable, at least not yet. They're not of a quality yet that we can invert them. So we need theory to simulate the dynamics, to predict the scattering patterns that we see and compare to experiment for a full interpretation of the experimental data. We can then do a comparable experiment in solution and in this case use techniques like time-resolved infrared spectroscopy to observe the photochemistry in a solvent environment. When we first published the data on the time-resolved spectroscopy, we concluded that the fast growth of the ketene must be from a concerted mechanism. But having now done the gas phase experiments, I think we were probably wrong, because we now know from the gas phase experiments that, and from the X-ray scattering, that the stepwise mechanism is still happening on a sub-picosecond timescale. So to us, to people working in the ultrafast community, sub-picosecond is a measurable timescale, so we can distinguish a truly concerted from a stepwise but still very fast mechanism. And I think in reality what we're seeing is a stepwise process in all cases. But we're able to demonstrate in solution that we're forming the carbene as an intermediate because we can trap it out chemically and isolate that species as proof that that is formed in the photochemistry. So let me finish there just by thanking lots of people. When you work with X-ray free electron lasers, you work with very large teams of people. So there are a lot of names here associated with the beam time that we had. I've highlighted the key players in red, and these are the people at Bristol that I've worked with on this project who've contributed in ways that I hope I've already told you about. So thank you very much indeed for listening, and I'll be happy to take questions.
Swayam Prabha, Digital India, Educated India.